So thank you for the introduction. I'm Samuel Drews, and this is work I've been doing with my advisors, Alsal Bergudi and Loris D'Antoni at the University of Wisconsin-Madison on repairing decision-making programs under uncertainty. And so before I dive into exactly what I mean by that, I want to inform you about a problem that's been receiving a lot of attention in the big data and machine learning communities, which is this problem of algorithmic fairness. And so the context is that in the modern era, there's a lot of decision-making that's being handled by automated processes through, machine-learned classifiers and whatnot. And on the one hand, this is nice because people are really bad at being objective, and so maybe an algorithm can do a really good job of that. But the question still remains that, can my machine-learned classifier somehow be racist or discriminatory? And in fact, there's been in the United States, for example, sort of a scandal in that an automated decision-making program used by the judicial system to determine whether or not someone is likely to commit a crime, and if so, basically whether they should be put in jail, was found through independent review to be disproportionately likely of incorrectly suggesting that African Americans would be likely to commit crimes. And so a number of people, decry this as, this is racist, this is a problem, and we need to do something about it. And that's where the motivation for this comes in, is that we have these algorithms and we want to reason about whether or not they're fair for some sense of the word. And so for an example way that we might, talk about the fairness of an algorithm is that suppose we have a decision-making program, this script D, that we're going to use to decide whether or not to hire someone for a job because this is the future and everything is automated. And so this decision-making procedure takes as input this vector of features V that describes the information about someone. So their age, their ethnicity, their years of college education, and things of that nature. And it'll spit out a decision, yes, hire this person, or no, don't hire this person. And in particular, this vector V is going to have a number of features, and one of them might indicate whether this person satisfies the minority status, for example, being African American. And so I've written this as a Hoare triple because we have this precondition that, I have this feature vector and I run it on my decision-making program, and I would like to verify some fairness property, such as this one at the bottom, which says that the probability that I hire someone given that they are a minority should be approximately the same as the probability that I would hire someone given that they're not a minority. And in fact, since we're talking about probabilities events, I don't just have a single input in my precondition. What I have is some kind of probabilistic description of the inputs that I'm going to run my program on. So specifically, this script M would be some kind of generative probabilistic program that when you run it, it spits out the features of a person, and if you ran it a bunch of times, the set of individuals that you would get as inputs would look like the population that you care about. And so this is a fairness verification problem of sorts, that we have this probabilistic property that we would like to verify. And in a separate piece of work that is conditionally accepted at OOPSLA later this year, we developed a tool called FairSquare, which is this kind of probabilistic verifier that can give you proofs or diffs proofs of those kinds of postconditions that involve probabilities of program outcomes. And so, when you get a proof that your decision-making program is fair, that's great, but sometimes they're not fair. And this is the case that we're concerned about in this work, is that when you get a proof of unfairness, what are you supposed to do about it? Because, we've shown that your hiring algorithm might be racist, but if this was obtained through machine learning, then, do you just keep machine learning with different algorithms until you happen to come up with a classifier that's fair? You can do that, but it's probably not a great idea. And so what we would like to do is somehow automate this thing where you take unfair programs and get fair ones. Or more generally, that you have programs that don't satisfy some probabilistic property, and you would like to have ones that do. So this is a setup for this problem of repairing decision-making programs under uncertainty. It's that we have some decision-making program D, where we have this probabilistic property that does not hold. And what we would like to find is a new program, D prime, that exists in some set of candidate programs we'd consider called the repair model, which is this Rm of D. And so what we want to find is this D prime in the repair model that does satisfy our postcondition. But there could be lots of programs that satisfy our postcondition, and so specifically what we want is one that is as close to the original program as possible. And for this notion of closeness, we're going to specifically use this difference function as a metric, which says that the difference between two programs is the probability that their outcomes are different, given that you sampled their input from the population. So for example, if two programs make the same decisions on everyone, then their difference would be 0. Or if they made opposite decisions on everyone, then this difference would be 1. So this gives you a sense of how close things are way weighted by the probability distribution that you're using for their inputs. And so to kind of visualize this repair problem, our repair model is this rectangular set of programs, and our initial program, which is unfair, is this .d. And there's some subset of our repair model, which are the set of programs that satisfy our post condition, and this is written as the oval. And so what we want to do is find, a program in this set post. But specifically, we would like to find this d prime that's as close to d as possible with respect to this difference metric. And in doing so, there's a number of challenges. First, the set of programs is potentially infinite. These are operating over, real valued inputs, and so there's uncountably infinitely many. And furthermore, we actually don't have any idea about how individual inputs should be related to outputs. Because, in general, if we're talking about machine learning, then the whole point of using machine learning is because it's really hard to come up with those relations between inputs and outputs yourself. And so what we need to be able to do is do this in an automated fashion. To make it more concrete, if my decision-making procedure is something like this, that takes as input someone's university rank, and if their university rank is in the top 10 schools, then you hire them. So if this is my decision-making program, then my repair model might be this skeleton of a program where I've taken my original one, but where I had those real valued constants before, I've introduced holes. And so a program in my repair model is any instantiation of the skeleton where I've replaced these holes with different real valued constants. And so how do I pick good real valued constants? To do that, we've developed an algorithm called DIGITS, which stands for Distribution Guided Inductive Synthesis. And it's kind of a stretch, but, catchy name. And DIGITS takes as input this problem where you have the precondition, a decision-making program, and a postcondition that it doesn't satisfy. And what it does is that it reduces this infinite behavior that we have to worry about to a finite behavior by sampling some finite number of inputs from this probabilistic precondition M. And using the samples, it generates constraints that it spits to a synthesizer that gives you various candidate programs that satisfy those constraints. And then so for each one of these candidate programs, repaired programs d prime, you need a probabilistic verifier such as FairSquare that'll tell you whether or not these candidate programs satisfy your postcondition. And it'll repeat this process and accumulate, a set of programs that happen to satisfy the postcondition, and eventually return the one that has the smallest distance from the correct program. In more detail, eventually it'll have sampled n inputs for some fixed n. And so these are, inputs 1 to input n. And so for each of these n inputs, it'll try all possible labelings of how you can relate these inputs to the outputs, true, hire this person, or false, don't hire this person. And so in total, there are 2 to the n many possible labelings or rows in this table. For each such row, you'll call your synthesizer. So in our implementation, we use a sketch-based approach with those kinds of skeletons. And so, for example, for this first row, which says, I need a program that hires person 1 and hires person 2, and so on and so forth, you'll get some program from your synthesizer, D1, that does exactly that. And we'll construct a program, similarly with a synthesis query, for each one of these 2 to the n rows. It may be that some of those sets of constraints are unsatisfiable because there is no program in your repair model that can do that, and that's fine, we'll just ignore that row. And then what you do is that you'll accumulate this set of potentially 2 to the n many programs, and you'll run your verification tool on each of those to determine whether or not these fairness tuples hold. And maybe we'll find that D2 and D5 don't satisfy the post condition, so we'll discard them. But ultimately what we'll have is a large collection of programs that do satisfy our post condition. We'll use the FairSquare, for example, to compute the distance of each one of these programs from the original one, and we'll output the one with the minimal distance. And that's the whole algorithm. To make it more concrete, how the sketch-based synthesis works is that if this is my repair model, then I'll translate it into a linear arithmetic formula where I've introduced variables for each of the holes. And this is just a formula that relates the inputs to the outputs. And so if I were to sample, 2 points, someone with university ranking 12 and 17, and I wanted to get a program consistent with hiring person 12 and not person 17, then I would take these formulas, conjoin them, and throw them at an SMT solver, and it might give me something like, well, if your first hole takes the value 10 and the second one takes the value 15, you get this program, which is exactly consistent with those constraints. And so you would do this synthesis query for every single one of the labelings, and then you would run that difference computation, and you would pick the best one. So that's the algorithm. And to see if it worked, we took a bunch of benchmarks from our verification tool, because believe it or not, some of our machine learned classifiers turned out to be unfair. And so these consisted of decision trees and support vector machines. And for each of these problems, we threw them at digits and gave it 10 minutes to try to find, repaired solutions that were as close as possible to the original one. And for every single one of our benchmarks, digits was able to find a repair. Some of them were farther away than others, but to look at one in particular, this is 10 different runs of digits on a single one of the benchmarks, one of the decision trees, where each run was started with a different random seed because that affects which samples you pick from your precondition M. And what you can see is that as you allow digits to have more samples, the distance of the best solution it has found tends to decrease. But it actually even seems like it's converging towards some limit, which in this case is about a 4% probability mass. So even across all of the different runs, they all seem to be approaching the same limit. And so that kind of poses the questions, is there a nice theoretical thing going on that is guaranteeing the convergence of digits? Because this kind of result is replicated across all of our benchmarks. And the answer to that is yes, given that you have a couple of nice properties. The first relates a well-studied notion in computational learning theory called the VC dimension of a set of classifiers to our problem domain. And the latter is kind of a somewhat complicated metric space definition that I'm not going to talk about in this talk. But if you're interested in it, then I highly encourage you to read our paper. But I would like to talk to you about this VC dimension, which is a notion of how expressive your set of candidate programs is. And so if my set of programs is, for example, two-dimensional linear classifiers, so if you fall on one side of a line, it decides to hire you, and if you fall on the other, it doesn't, then if you give me 3 points for these, for example, and say, hire these ones I've colored black and not the one I've left blank, then I can give you a line that separates them accordingly. In fact, for these 3 points, no matter how you want me to label them, I can always find a line that does that. And so the set of two-dimensional linear separators has VC dimension 3. And so this finite VC dimension says something about that your set of programs isn't so expressive that it can do whatever it wants. And so for the convergence of digits, we rely that you have this finite VC dimension property, and we assume that there exists some best solution in your repair model so that it satisfies the postcondition, and it is optimally close to the original program. And so our convergence result is basically, again from computational learning theory, the result of pack learning. And it basically says that with high probability, you can get arbitrarily close to this optimal solution if you're willing to use enough samples that's polynomials in these various parameters, the finite VC dimension and these precision constraints. And I just want to point out that whenever you have a repair model that can be written as a linear arithmetic formula with a finite number of holes, those all have finite VC dimension. And so this usually applies. To give kind of a more intuitive illustration of what's going on here, it's that we have this repair model, which is this rectangle, right? And when we sample a single point and say, I want to consider a program that hires this person and a program that doesn't hire this person, what we're doing is that we're splitting the space of possible repairs into 2 halves. One half where, these are the programs that hire this individual, and the other half is the ones that don't. And digits simply picks a single program from each of these regions, which are these gray dots. And so with one sample, you have 2 regions. If I have 2 samples, then there's 4 labelings, and so I've split my repair model into 4 regions. With 3 samples, 8 regions, and so on and so forth. But the idea is that if you have these nice properties, then for a sufficiently large number of samples, what you'll encounter is that for at least one of your labelings, the entire set of programs consistent with that labeling will be contained inside of your postcondition. And then furthermore, you can actually bound, the distance of all of them from the optimal solution. So even if your synthesizer is somehow adversarial, it actually can't ruin this. It has to give you a program that is correct and close to the optimal solution. And so the other thing that really makes our digits work is that we have an efficient implementation that is inspired from some concepts of DPLL and CDCL. And so instead of enumerating all 2 to the n ways of labeling some samples a priori, what we do is that we pick samples one at a time and maintain this Trie structure. And so each node in this Trie is going to be a program. And so initially we have our root, which is the program that we start with. And when we sample a single point, we add height to our Trie. And so what this says is that if I take this path down the left, that's saying that give me a program at this leftmost node that doesn't hire this person that I've sampled with S1. And on the right, that's someone that give me a program that does hire person S1. And then I would sample another point, and I would extend my trie as follows, where again, paths correspond to sets of constraints that the programs at those nodes must satisfy. And so you might think this is kind of odd, because instead of enumerating 2 to the n many programs, we're now having to enumerate 2 to the n plus 1. But it turns out, for example, that I'm now going to refer to programs by colors. That if my initial program is this blue program, it already makes a decision about whether or not to hire person S1. And so if my decision-making program does hire S1, then actually when I follow that path to this node, I don't need to run another synthesis query. I can just use my original program in this place. And similarly, if it happens that my original program doesn't hire S2, then this other node can also be filled with the blue program. In fact, in general, it's always the case that when you have a program at a node, one of its children you can propagate your solution at that node to one of its children, because one of those decisions is already going to be consistent with it. So we maintain that you actually only need to run queries for 2 to the n many programs still. The other important thing that we do is that if you find that there is no solution for a particular node, no program consistent with that set of constraints, then we will prune that subtrie from there and not try to explore any programs in that region. And then furthermore, what we'll do is that we'll try to generalize from those constraints that led to being unsatisfiable and hopefully prune other parts of the tree as well. And so these optimizations turned out to be a really good thing to do in practice. This is a plot for one of our benchmarks where the red line denotes how long it takes to run digits on n samples if you just explicitly enumerates the 2 to the n many things. Where the blue line below indicates how long it takes to explore the Trie structure up to depth n. And as you can see, as the number of samples scales, that it is drastically better to use the Trie structure because of these savings that you experience. And this result, again, is observed across all of our benchmarks. So to conclude, I just want to recap that I try to motivate you with this problem of algorithmic fairness by casting it as a probabilistic property of programs. And we presented an algorithm, digits, that automatically repairs it by reducing infinite amounts of behavior to finite representative samples. And the convergence is really rooted in these core concepts of computational learning theory. I'm a little over time, but I'll take any questions you have. Thanks.
What's the impact of these repairs on prediction accuracy?
That's a good question. So we didn't explicitly compute it, but usually those methods of determining like the accuracy come from running it on some corpus of training data. And if you assume that your precondition is a distribution that represents that data, then the semantic distance, this difference function that we use between the two programs, bounds how much worse that classification can be. Because if I'm only different on 4% of probability mass, I'm probably only 4% worse on classification. Does that make sense?
Yes, although I don't quite buy that in practice. You can make the assumption that your precondition is going to be a faithful representation of the training data. Those distributions are likely to be extremely complex.
Right. But the other thing that kind of arises is that so this is well studied that you have this trade-off between satisfying some kind of fairness property, or in general some kind of formal property on your classifier. That there's a trade-off of those things with classification accuracy. So that's
sure. So actually a more general question is that why wouldn't you do all of this at training time? Because at this point what you're doing is that you are training a classifier, right? And then you're throwing away the data and you're doing all of this stuff to repair it, right, post-fact. But it seems to me that a more natural approach is to just introduce the fairness constraints at training time when you also have the data at hand, so you can really do a multi-objective optimization of trying to fit the data set while also trying to fit the fairness properties as much as possible.
Right. So I guess so my answer to that is twofold. The first is that to our knowledge there isn't really existing work in the machine learning community on how to do this kind of machine learning while maintaining other properties than just empirical structural error minimization and things of that nature. Although there has been some work on how
I mean, it's optimization, right? So
Yeah,
there is work on constraint optimization. Maybe we can take this offline.
But then the other half is that we're more general than just that, because if you can provide, arbitrary skeletons of programs, then you can, and arbitrary properties, then you can sort of just do whatever.
Sure. Okay. Thank you.